After analyzing the visual characteristics of the design object, selecting the appropriate lighting method, determine the required luminance and quality indicators, and selecting the light source and lamps, the lighting calculation stage is entered, and the required single light source power is obtained, or check whether the illuminance meets the standard according to the predetermined single lamp power. Lighting calculation commonly use the utilization coefficient method. The utilization factor Cu is equal to the ratio of the effective luminous flux Φu that the light source actually projects to the working surface, and the rated luminous flux N∅ of all light source. A part of luminous flux emitted by the light source is absorbed by the lampshade. A part is directed to the work surface to form direct illumination. A part is projected to other surface in the room and reflected to the work surface to form reflected illumination. Then the effective luminous flux Φu actually projected by the light source to the working surface is equal to the sum of the direct luminous flux Φd and the reflected luminous flux Φp. The larger the effective luminous flux, the more the luminous flux emitted by the light source is utilized, and the larger the utilization factor is. The main factors affecting the utilization coefficient are, first, lamp type and lighting method. Since there is no loss of direct light luminous flux, the direct type is more conductive to the utilization of light than other types of lamps. Second, lamp efficiency. The higher the efficiency of the luminary, the more luminous flux is obtained on the work surface. Third, the light reflectance of the interior surface of the room and interior facilities. The higher the light reflectance, the more reflected light flux. Fourth, room size. As can be seen from the small figure below, the direct luminous flux of the same lamp in the rooms of different scales is different, and the wide and short room is larger than the thin and high room. It can be seen that the ratio of the working surface to other surface of the room is highly larger. The more direct luminous flux is received, and the greater the utilization factor is. As can be seen from the big picture above, the indoor luminous flux distribution is divided into three spaces by the installation height line of the lamps and the working surface. From top to bottom are ceiling space, the room space, and the floor space. The reflectivity of each space is represented by the ceiling space ratio CCR, the room space ratio RCR, and the floor space ratio FCR. Then the average illuminance E on the working surface is equal to the effective luminous flux divided by the working surface area. Among them, the effective luminous flux is equal to the number of lamps multiplied by the utilization factor and the rated luminous flux of a single lamp. Considering the population and the light delay of lighting facilities during use, the maintenance coefficient K is introduced to increase the internal illuminance, and then the lighting calculation formula using the coefficient method is obtained. Using this formula, the number of lamps can be obtained when the power of a single lamp has been determined. When the number of the lamps has been determined, the single lamp flux can be determined, and then the single lamp power can be determined. Take the classroom as an example for calculation. It is known that the length, width, and height of the classroom are 9.6 meter, 6.6 meter, and 3.6 meter, of which 3.6 meter is the clearance size. There are 3 windows, 3 meter wide and 2.4 meter high on one side wall, and the desk height is 0.8 meter. First step, according to the room function, determine the average value of the illuminance on the desk to be 300 lux for the classroom. In the second step, according to the function of the room, 40-watt cool white fluorescent lamp was selected as the light source for the classroom, and the rated luminous flux was found to be 2650 lumen. Third step, select direct lamps according to the light source and classroom. Determine the hanging height of the lamps to be 0.5 meter, according to the size and structure of the classroom. Find the type of lamps and the corresponding distance to height ratio, and the maximum value in the BB direction of the vertical lamp tube is 1.6. The maximum value of the AA direction of the parallel lamp is 1.2. Fourth step, determine the light reflectance of interior surface. Find that the ceiling is 0.7, the wall is 0.5, and the floor is 0.2. Fifth step, find the room space ratio RCR. The calculated height of the lamp HRC is equal to the room net height of 3.6 minus the dusk height of 0.8. And then minus the lamp hanging height of 0.5, which is equal to 2.3 meter. Substitute the length and width of the classroom and the HRC value into the RCR formula and find that the RCR is equal to 2.94. Sixth step, find the average light reflectance of room space. Assume that the light reflectance of the window is 0.15. Calculate the product of the area and the light reflectance of the wall and the window respectively, and divide the sum by the total area, which is approximately equal to 0.4. The seventh step is to find the light reflectance of the effective ceiling space. First, the ceiling space ratio CCR is approximately equal to 0.64. Then, according to the ceiling light reflection ratio of 0.7, the wall light reflection ratio of 0.5, and the CCR value of 0.64, the average light reflection ratio of the effective ceiling space is 0.62. In the eighth step, according to the RCR of 3, the average light reflectance ratio of the room space of 0.4, the average light reflectance ratio of effective ceiling space of 0.62, the utilization coefficient was found to be 0.604. Ninth step, find out the maintenance factor K is 0.8. Tenth step, substitute luminance 300. Room length 9.6 and width 6.6. Luminance flux 2650. Utilization coefficient 0.604 and K value 0.8 into the lighting calculation formula using the coefficient method to obtain 15 lamps. The 11th step, according to the distance to height ratio found in the previous second step, and the calculated height of the lamp 2.3 meter, the maximum lamp distance in the BB direction of the vertical lamp tube is 3.69 meter. And the maximum lamp distance in the AA direction of the parallel lamp tube direction is 2.76 meter. According to the calculation results and room size and considering the placement area of the desk, the lighting layout can be drawn. The 12th step, finally, we check whether the calculation results conforms to the current value of lighting power density of 11 watt per square meter by calculating the lighting power density. The electronic baluster matching the fluorescent lamp is calculated as 4 watt. The installation power of a single lamp is equal to the rated power of the light source 40 watt plus the baluster power 4 watt. Multiplied by the number of lamps 15 to get the total lighting installation power, divided by the classroom area, the lighting power density of the classroom is 10.4 watt per square meter. Since the calculation result is less than 11, it can be determined that the lighting design is feasible. Think about it. Can you use the lighting power density value to simplify the lighting calculation and directly calculate the number of lamps? Can this calculation method be used for other 3 lighting methods?